Welcome to this explainer on what I really like to call the invisible scaffolding of modern civilization, measurement. Seriously, think about it. Every bridge you drive over, every GPS direction you follow on your phone, and every medical dose you take is built upon an incredibly precise, universally agreed upon foundation. So today we're diving into the fascinating world of precision metrology, and we're going to see exactly how humanity learned to measure the universe with some truly mind-bending exactness.
To kick things off, let me ask you something. How long is a second, really? Or a meter, for that matter? Well, the speed of light in a vacuum is exactly 299,792,458 meters per second. And that isn't some rough estimate, it is a perfectly exact, defined constant. Because of that fact, a meter is officially defined as the distance light travels in exactly 1/299,792,458 of a second. So we're plunging right into the sheer exactness of the universe here, where the speed of light itself is literally what dictates our rulers.
Okay, let's jump into section 1, the heartbeat of physics. We're going to look at why physics has to be a purely quantitative science. You know, it's just not enough to look up and say a star is very far away, right? We need precise, reproducible numbers if we want to make any real progress. A physical quantity is the exact concept that separated the natural philosophy of the ancient Greeks from actual modern science. The Greeks loved to ponder the nature of matter philosophically, sure, but science truly began when Galileo actually timed the swing of a pendulum and measured the distance of falling objects. Measuring physical quantities is what finally gave physics its predictive power. And when we measure, we have to categorize. Now, while human attributes like beauty or happiness are completely subjective, physics demands rigorous precision, and it gets there through scalar and vector quantities. A scalar quantity is fully described by just a number in a unit, like a 5-kilogram mass. It's simple, but a vector quantity requires both magnitude and direction to even make sense. Saying you have 30 newtons of force is incomplete. You have to say 30 newtons directed upward for it to actually mean something in physics. Moving right along to section 2, from pharaohs to Paris. Let's trace the remarkably chaotic evolution of our measurement standards. Historically, humanity was kind of all over the place. We started with these highly inconsistent body-based units. Take the ancient Egyptian cubit, for example, which was just the length from the elbow to the tip of the middle finger. But obviously, a pharaoh's arm is going to be pretty different from a commoner's arm, which made trade and science incredibly frustrating and inconsistent. It actually wasn't until the French Revolution in 1791 that a rational, nature-based metric system was established. That big shift eventually led to the 1875 meter convention, and finally, the establishment of the modern SI system we use today in 1960. It was a long journey from chaotic body parts to a unified global language. Which brings us to section 3, the 2019 measurement revolution. This was literally the biggest redefinition of the SI system in an entire century.
To really understand why this revolution had to happen, think about this alien thought experiment for a second. For the longest time, we defined our units using physical artifacts or local substances. For instance, the Kelvin relied on the triple point of water. But what if we encounter an alien civilization that has no water? How on earth do we communicate temperature to them? It highlighted a profound problem. Defining universal measurements based on localized physical objects is just inherently flawed.
There's a really stark contrast when you look at how things changed in 2019. The global scientific community completely shifted away from physical objects. We replaced the international prototype of the kilogram, which, believe it or not, was a physical, scratchable metal cylinder kept in a literal vault in France, with the eternal Planck constant. We swapped out water for the Boltzmann constant. We finally grounded our most vital measurements in the absolute, unchanging constants of nature, making the SI system truly universal. All right, section 4, the art of exactness. Let's talk about how scientists actually navigate the persistent enemy of every single experiment, uncertainty. The very first concept to wrap your head around here is systematic error. Now, unlike random blunders that fluctuate back and forth, systematic errors are these consistent inaccuracies that always push a measurement in the exact same direction. Think of using a stretched out ruler or an ammeter that reads a current even when it's completely turned off. The absolutely crucial takeaway here is that taking 100 more readings won't do a thing to fix a systematic error. You can't average it away. It requires careful, deliberate calibration. And this brilliantly illustrates the difference between two terms that people mix up all the time: accuracy versus precision. Picture throwing darts at a dartboard.
Accuracy is how close your measurement hits to the true value, the bullseye. Precision, on the other hand, is just how reproducible your measurements are. If you land all your darts in a super tight cluster, you actually have high precision, even if that entire cluster is completely off-center in the corner of the board.
To keep all these measurements mathematically honest, physicists use a clever tool called dimensional analysis. This basically guarantees that the fundamental rules of the universe are respected in our math. For instance, you absolutely cannot equate momentum with energy because their underlying dimensions of mass, length, and time simply do not match up. If the dimensions don't balance out perfectly, your physical equation just isn't physically real.
Which takes us to Section 5, the quantum frontier. This is the awe-inspiring, mind-bending edge of modern measurement.
Classical measurements are totally boxed in by strict rules, specifically something called the classical shot noise limit, where precision only scales by the square root of the number of measurements. But using quantum metrology, we are smashing right through those classical limits. By utilizing crazy quantum phenomena like spin-squeezed states and quantum entanglement, we can push precision to scale proportionally to n, reaching what physicists call the Heisenberg limit.
The most incredible application of this tech? Optical atomic clocks. Teams at MIT and NIST are actively building these devices right now. By upgrading from standard microwave frequencies up to vastly higher visible light frequencies, they can harness energy transitions in specific atoms like ytterbium or strontium. This drastically reduces quantum noise. They are literally slicing time into unimaginably small, highly stable fractions.
So the crucial point I want you to take away is that this isn't just some abstract physics experiment. These are visceral, high-stakes realities that affect us every day. Just a 1 nanosecond error in a GPS atomic clock translates to a 30-centimeter positional error on your phone. Optical clocks are now so precise they can detect a 1-centimeter change in gravity. From tracking exact millimeters of climate-driven sea level rise, to building jet engines to strict micrometer tolerances, to ensuring your medicine is dosed strictly down to the mole, modern survival literally depends on this level of exactness.
And right now, we've achieved something truly staggering. Optical atomic clocks have reached the 18th decimal digit of precision. Just let that sink in for a second. The 18th decimal digit. They are officially the most accurate devices humans have ever built in all of history.
There's this quote that just perfectly captures our entire journey. To measure more precisely is to understand nature more deeply. When you think about it, moving from using the length of a pharaoh's elbow to relying on the quantum entangled states of ytterbium atoms, the evolution of precision metrology perfectly mirrors humanity's entire intellectual ascent. Every single time we sharpen our rulers, we peel back another hidden layer of the universe.
Which leaves us with a final, completely thrilling thought. With instruments now probing reality at the 18th decimal place, we're no longer just measuring the world we know. We have to wonder, will this unprecedented, mind-boggling level of precision finally unlock the secrets of dark matter and reveal the new physics hiding beyond the standard model? Well, only time, measured very, very precisely, will tell.